Hello everyone, my name is Momen Oqaily. I'm a PhD graduate from Concordia University, and today I'll present ChainPatrol, balancing attack detection and classification with performance overhead for service function chains using virtual trailer auditing and network function virtualization. So the outlines for my presentation today are the background, the motivation and overview, the related work, and then I'll discuss the ChainPatrol methodology and the experiments, and finally I'll conclude this presentation. So network function virtualization has emerged as innovative networking architecture that aims to overcome the limitations of traditional networks through decoupling the network functions from property physical boxes and run them as virtualized software applications on top of commodity hardware. The NFV aims to increase availability and flexibility to try new services and to provide on-demand service provisioning in a pay-as-you-go billing manner. The NFV market will grow by almost 35% each year, reaching 122 billion by 2027, according to a forecast from the Research and Market. So although NFV has been widely adopted and proposed as a promising solution, there are some security concerns regarding outsourcing mission-critical applications to third-party clouds, such as the vulnerabilities in the network function software and the protocol stack, the misconfigurations and attack in the underlying infrastructure, and also that tenants usually like direct access and control to the infrastructure, causing invisible attacks and breaches to the tenant's policies. And to make things worse, the provider may not be aware of each tenant's specific requirements, and hence they can't do the auditing on their behalf. So in order to understand those challenges, let's assume that we have the following service function chain where we have 3 virtual network functions, and the tenant specifies that the traffic should pass through each network function before reaching the destination. So here the traffic has to go through the firewall first, and then the IDS, and then the DPI before it reaches the destination. Let's also assume that we have an attacker who was able to compromise the vulnerability in the operating system of the underlying switches and took control of them. Then this attacker can perform a wide set of attacks silently without being detected. So for example, this attacker can bypass one or multiple virtual network functions in the chain. He can also perform packet dropping, redirection, injection, and even man-in-the-middle attack. So in the next slide, I'm going to discuss the motivation behind this work and a high-level overview of our solution before I go into the details. So if the attacker compromises any of the underlying switches and become able to perform any of the previous attack I mentioned in the previous slide, then the tenant has no direct access to the cloud-level resources to perform any sort of auditing or verification. Also, the cloud provider is not necessarily aware of all the tenant service function chain and forwarding path policies to perform the auditing on their behalf. So the existing solutions in the literature add a physical trailer to every packet at the source that will be verified at the destination. And this trailer contains 2 identifiers for the packet and the flow, and the MAC computed over the packet itself with those 2 identifiers. Now, if the attacker wants to perform any of the previous mentioned attacks, he won't be able to do so because he does not have the key to calculate the trailer for the newly injected packet. So up to this end, adding crypto trailers to every packet may incur significant communication overhead, for example, up to 30% for DNS traffic. And the challenge here is how to detect breaches to service function chain integrity in the underlying infrastructure without the communication overhead of the crypto trailer-based solutions. So our idea was to virtualize the trailers as side channel watermark using the inter-packet delay while keeping the same crypto trailer design to ensure provable integrity protection. And if we were able to do so, we will reduce the communication overhead to 0 as no extra bit will be added to the packets. So to understand our high-level idea, let's assume that we have a crypto trailer of 0, 1, and we want to encode it into those 4 packets, where larger than usual inter-packet delay means 1 and smaller means 0. So if we were able to delay packet P4 and packet P1 to inject this watermark, then now if the attacker wants to inject a malicious packet between packet P3 and P4, we will be able to detect it at the destination because he corrupted the virtual trailer that we inserted between those packets. So up to this end, sending crypto trailers via a side channel provides the best of both worlds. We have provable attack detection from the crypto part, and we have 0 communication overhead because of the information sent using the side channel. So the question now becomes how we can encode a 260 265-bit MAC inside such a limited channel. Before I discuss how we're going to do that, I will first go quickly through the related works. So as you can see in this table, I compare ChainPatrol to the most existing solution in the literature. And as we can see, ChainPatrol is a runtime online solution where some of the existing solutions are offline. Also, some of the existing solutions are using crypto-based or formal method-based techniques. However, in ChainPatrol, we are using crypto and side channel-based method. Also, ChainPatrol is a black box auditing solution, meaning that we don't require any access to the cloud provider resources, and also we don't require any modification to the VNF software itself or to the cloud provider infrastructure. And also, we are covering most of the existing attacks in the literature, unlike some of the existing solutions who clearly state that they can detect some of the attacks. So in the next slide, I'm going to discuss the ChainPatrol methodology. So our goal is to design the virtual trailer with the same information as in the physical trailer to support the attack detection and the classification. And this is a challenging task because unlike the physical trailer, which can be identified for each packet, a virtual trailer can only be encoded in the IPDs of multiple packets. So to address this challenge, we designed our virtual trailer to be encoded in the IPDs of multiple packets such that the MAC is computed over an equal-sized group of consecutive packets inside the same flow. We call it as a super block, while each super block consists of equally sized group of blocks. And inside each block, we have 3 frames, one to identify the block number, one to identify the flow number, and one to carry part of the MAC. So if we follow this design and we want to encode a MAC into a block, we have to delay this block until the entire super block arrives. And this is because the MAC is computed over a super block, so it cannot be computed before the entire super block is received. But doing so will cause prohibitive delay that we should avoid. So in order to solve this issue, we encode the watermark of each block in the corresponding block of the next super block. This would allow us to compute the virtual trailer, which tells us how to modify the interpacket delays of the next super block ahead of arrival of this block. So we'll be able to modify the IPDs as soon as each block arrives and forward it with minimum delay. So in this slide, I'm going to discuss the attack detection methodology using an example. So let's assume that we have those 3 super blocks received at the destination and we want to verify them. In the first iteration, the attack detection window slide over the first 2 blocks. And let's assume that the first expected virtual trailer will be the block number equal 1, the flow ID 1, and the MAC value is 1001. The virtual trailer encoded from super block 2 contains the same block number, flow ID, and the MAC values. So as a result, the first half will successfully match, and then the super block 1 can be marked as recovered as no attack is detected. Now, in the second iteration, the attack detection window slide over the next 2 super block 2 and 3. And let's assume now the block number we are looking for is 4, and the flow ID is 1, and the MAC we are looking for is 0010. So as we can see, the virtual trailer decoded from super block 3 contains the same block number and flow ID. However, the expected MAC value does not match. So at this point, it's unclear for us if the attack happened to super block 2 or to the virtual trailer decoded from super block 3. So at this point, we mark both super block 2 and super block 3 as attacked. So in this slide, I'm going to discuss our attack classification methodology. So in this table, we describe the attack types and their classification rule based on the reconstruction of the virtual trailers. And as you can see, we have 4 levels of classification. We have packet, block, and flow and service function chain levels. And for each level, we have a group of attacks and their classification rule based on the decoded virtual trailer at the destination. So to better understand the attack classification, let's take an example. So in table A, we have a list of the expected virtual trailer. And in table B, we show the virtual trailer decoded and marked by the attack detection algorithm, while in table C, we show the virtual trailer recovered by the attack classification algorithm. So I'll explain how we can classify one of the attacks using these tables. So the classification algorithm detects reordering attack of the first 2 shaded blocks in table C. And this is because the block number fields are out of order, and the rule of block reordering leads to a successful reconstruction. So in the next slide, I'm going to go briefly about and discuss our experiments. So ChainPatrol was deployed in Amazon EC2 using T3 small type instances. and each instance run Amazon Linux 2. And our evaluation leverages two datasets, a public cyber defense dataset and the live traffic of our in-house 5G core testbed to collect realistic IBD values. So in the first experiments, we evaluated the parameters selection for ChainPatrol, and our results show that we are able to achieve 100% extraction rate if the parameters are selected carefully. And this is because the network connection between two VNFs in data center is usually more stable compared to the internet. And in the second set of experiments, we evaluate the impact of the superblock size and the packet size on the end-to-end delay. And our results show that they have almost no impact because the virtual trailer of the superblock I is always encoded in the next superblock. And also the virtual trailer extraction and verification at the destination do not intercept the packet. We also evaluate the attack detection and the classification accuracy, and our results show that the attack detection accuracy is at 100%, and as the watermark are 100% extracted at the destination, and the classification accuracy is around 70% due to much smaller number of trailers compared to the physical trailer solutions. We also evaluate the attack detection time, and our results show that the detection time has no impact on the service delay due to the multi-threading implementation of ChainPatrol. So, as a conclusion, in this work, we propose a novel concept, the virtual trailer, which leverages the interpacket delay as side channel to encode cryptographic trailers without adding extra bits to the packets. And we developed ChainPatrol, which is a solution for encoding and decoding virtual trailers and detecting and classifying various service function chain attacks based on virtual trailers. And finally, we implemented and deployed ChainPatrol based on Amazon EC2, and our experimental results confirmed its effectiveness and efficiency. Thank you so much.